In this video, I'm going to be talking about linear transformations in linear algebra, which is a very core concept to the subject itself. And to start off, we're just going to define what a linear transformation is in the formal mathematical sense. So we define a function t as a linear transformation if it's mapping from a vector space V to W and the two following conditions are satisfied. The two conditions are if we add two vectors v1 and v2, then apply this linear transformation. This should be equal to first applying the linear transformation to v1 and then adding it to the linear transformation applied to v2. So that's first condition. And then the second one is that if we have some constant c and we multiply it by v1 and then apply the linear transformation, this should be equal to first just applying the linear transformation to v1 itself and then multiplying that by the constant. So this is how we define a linear transformation. So any function that's mapping from one vector space to another that satisfies these two conditions is a linear transformation. And that's just how we define it. Now, an important thing to remember is that a linear transformation is actually just a function. And this is something that I said just at the very start of the video. But what that means is no matter what input you give, you can't get two different outputs. So any input you give maps to one specific output. You might have two different inputs that map to the same output, but you can't ever have one input that gives you two different outputs. And that's the nature of a function in general, right? And since a linear transformation is a function, that should follow. So now I'm going to give an example of probably the most boring linear transformation, but just something to show that the conditions actually do hold for what we define a linear transformation as. So let's take the matrix 1, 0, 0, 1. This is a linear transformation, so we can call this T. Now, if we apply this linear transformation to any vector, if we have the vector, say x, y, and then we apply this linear transformation, we just get x, y back. And that's why I said that this linear transformation is very boring. It just spits out what you give it in. So this is a linear transformation that maps all points x, y to themselves. But this does satisfy the conditions for a linear transformation, and we're going to go ahead and just run through those just to show that it holds. So let's take our vector 1 as x1, y1, and vector 2 as x2, y2. Now, the first thing that we need to check is the addition condition. So let's try this, where we do t v1 plus v2. So v1 plus v2 in this case is going to be x1 plus x2, and then y1 plus y2. So this is this here, just sum. And we want to apply the linear transformation to it. And if we apply the linear transformation to it, because we know that this just spits out whatever you get, it's going to be this itself. So if we do the linear transformation on this, we just get this back. So that's something to note. And then we're going to try it on the two vectors separately and add them together and see if we get the same thing. So if we do tv1 plus tv2, let's think about it. tv1 is going to give us x1, y1. So we have x1, y1 plus tv2, which is going to give us x2, y2. And of course, that's going to give us x1 plus x2, y1 plus y2. And these are equal. So the first condition is satisfied, the addition condition. So now all we have to check is the multiplication, see if that holds. And of course it should, but we just want to show it. So what we're going to do is we're going to take, say, CV2, right? And we're going to do T v1 times 2. T v1 is just going to give us x1, y1 as before. And times 2 gives us 2x1, 2y1, right? So now we need to check that it holds if we put that constant inside of the parentheses. So if we do c times v1, we get, if we do c times v1, we get 2x1, 2x2, or 2y2. Oops, I mean 2y1. Yeah, 2x1, 2y1. And then of course, if we apply t to this, we just get 2x1, 2y1. And these are equal here, so both conditions are satisfied, and this is indeed a linear transformation. So that's just a check of a very basic example, but just something to show how you can show something is a linear transformation and something that we expect to be a linear transformation being verified to be one. So now let's do something that's slightly more interesting. What would happen if we took a matrix, say 0, 1, 1, 0. Now, this is also going to be a linear transformation, and I'm not going to go through the steps to show that it is, but the addition and multiplication conditions will hold. But if we multiply a vector xy, then we're going to get the vector y, x. So this is still a pretty basic transformation, but it's a little more interesting. There's something that you can actually think about happening on the graph. In the last one, we just had the graph going to the graph, or R2 going to R2, right? Because all the points in R2 were just being mapped to themselves. Even though there was actually a transformation happening, you couldn't really see anything because nothing was moving. In this case, let's think about if you have like a point. I'm actually gonna erase this just to give it a little more space, but let's think about if we have our graph and we take the point 2, 2, 1, right? So this is 2, 1 here. And then if we apply t, it's gonna move our point to 1, 2. And 1, 2 is gonna be somewhere here. Now what's actually happening here is the points are getting flipped across the line x equals y. If you imagine that just being right here, and then our original point 2, 1, 2, 1 be somewhere right here, you can imagine all the points getting flipped over this line. So that's what's going to happen to all the points in R2 when we apply this linear transformation. That's a little more interesting. It's a simple linear transformation, but something's actually happening here. So all the points are just getting flipped across this xy axis. Now what might happen if we take one linear transformation where, say we have 1, 0, 0, 0. Now if we multiply any vector x, y by this, then we're just going to get the x value, and then a 0 for y, no matter what you plug in. So this one is going to do a different transformation. This one is going to collapse the values onto the x-axis. So you can imagine this being at 2, 1 gets mapped to 2, 0, which is going to be right there. So this is another kind of linear transformation. But yeah, all the points here are going to follow this same pattern. And that's what you can think of a linear transformation as. It follows the name. I mean, you can think of lines, like a line here, getting collapsed down onto the x-axis. So that's kind of the general idea of what's going to happen with linear transformations. And it's kind of interesting. And there's all kinds of things that you can do, but these are just basic examples to show what it might look like in the most concrete sense, or the easiest thing to see. So now we're going to move on to another idea, which was kind of implicitly shown in the last few examples, but something that's important to note. If you have a linear transformation that we call like t of x, then there's a matrix A where t of x is equal to A times x. And basically what this is saying is that all linear transformations can be represented by matrix. This is something that we expect to be true because in my previous examples, I was using matrices to represent linear transformations. So here is a little bit of a different problem, but we are given a linear transformation and we want to find the matrix A that defines the linear transformation. And we know that there has to exist a matrix A where we can get this output, because each linear transformation can be represented by a matrix. So this linear transformation is going from R2 to R3, and this is a little different than the other examples I did where I was going from the plane R2 to the points were getting mapped to somewhere else in R2. You don't have to be going from like R2 to R2 or like R3 to R3. You just have to be going from vector space to vector space. So these could be like more abstract vector spaces, but I think the best way to think about it here is just think about in Rn, because it's kind of the most standard way you would think about linear transformations and the most intuitive. But yeah, so I'm going to be sticking to that when I'm doing the explanations here. But yeah, that's something to know. This is going from R2 to R3, right? So we want to find this matrix, and how we're going to do that is we're going to think about the basis vectors. Because if we can figure out how the basis vectors are getting, or the standard basis vectors, if we can think about how the standard basis vectors are getting transformed, then we can describe the behavior of all the other points when they get transformed. And this kind of makes sense with the way that the addition and multiplication were defined for a linear transformation. Because if you think about the linear transformation applied to the standard basis vector for R2, the standard basis vectors, where you have like 1, 0, and then t of 0, 1. This is going to be the same as t of 1, 0 plus 0, 1, but then also this would apply with scalar multiples as well. Because the 1, 0, and 0, 1, these are the standard basis vectors for R2, so that means that you can take all the possible linear combinations and cover R2 by scaling and adding them. And this is preserved under the conditions of a linear transformation. So that's why we can kind of describe the whole behavior of the transformation just by the basis vectors themselves. And for this problem in particular, that's going to be very helpful. So how we do it is we're going to take our first basis vector, which is 1, 0, and 0, 1. And like I said, these are the basis vectors for R2. And we're going to look at how they're being transformed. We see that x in this first row, we have 2, and then we have 1, 1. So we want to see how the base vector here is getting transformed. And it's going to be done by this, where we have, say, 1, 0 is going to correspond to 1 times 2, 1 times 1, 1 times 1. So, and then we're going to have something here, something here, something here. But if we multiply 1, 0, this base vector, by this, then all the x values match up here, or the coefficients match up. And now we need to figure out what it's going to be for our y, which the basis vector is 0, 1, and we have 3, negative 1, 0. So you can imagine it's just 3, negative 1, 0. And this is exactly the matrix A that defines the linear transformation. So that's how we can go about it, just thinking about the basis vectors and kind of the behavior, and knowing that they can define the rest of the linear transformation. If you just use them, you can figure out that matrix A that defines the linear transformation. So that's most of what I wanted to cover, but hopefully this was helpful, and hopefully it gives you a better grasp on what might actually be happening when you're applying linear transformation, or you see it in like a homework problem or something like that. But yeah, thank you for watching.